Honestly, each time I look at that scenery, it's just exciting to see the Swiss mountains. But I have a guest today, and I'm happy to welcome Luis to this episode today. Hi, Luis.
Hey, Stefan, how's it going? And welcome to everyone else. Thank you for spending this evening listening about nerdy things like transformers.
Nerdy things. That sounds absolutely amazing. We're really looking forward to it. And as I said, there's so many people have signed up for this evening session. So I guess your attention is fully promised for this evening, I tell you. Luis, but just a little bit about you. So we talked a bit before we started today. So I think you were traveling around the world a little bit. So where did you lived in your life?
Yeah, sure. It's a long story, but I'll give you the short version. I was born in South Africa, and then spent half my childhood in Chile in South America, and then the other half in Tasmania in Australia, which is basically the end of the world. And when I was a kid, I kind of got interested in physics, and so I decided to study this at university. And in the process of doing that, I ended up in Switzerland developing quantum mechanical theories to study the Large Hadron Collider, or the data coming from the Large Hadron Collider. And it was at this point where my office mate showed me he was developing a machine learning model to basically detect events in the collider. And he kind of kicked the crap out of all my mathematical modeling with about 3 lines of TensorFlow. And so at this point, I started getting really interested in machine learning because it offered a kind of completely different way of thinking about scientific problems. And then I had an opportunity to join a startup in Bern in Switzerland. And so I thought it was a good time to switch to industry. And fast forward a few years, I'm now working at Hackingface as a machine learning engineer in the open source team.
That's interesting. Hackingface, how large is the community? You're actually colleagues. How many colleagues do you have?
So at the moment, we're around 60 people. And the company has grown very fast this year with the Series B funding. Cool. So I think it's roughly tripled in size since the start of the year. And there's a much wider community of people who interact with the open source ecosystem around Hugging Face. And this ranges from, say, 5,000 companies, but obviously many more individuals who are playing with NLP and computer vision in their kind of day-to-day work.
Yeah, awesome. And just because we have a lot of people here, just one job questions. Are you still looking for people?
Yes, we're still hiring. I can send a link later. Basically, it's angellist.co. If you look at Hugging Face, there are various jobs ranging from engineering to sales to developer advocacy. So if you're interested, just send an application or just send me a message on Twitter or email.
Yeah, awesome. So good evening as well. So it's evening at least here. So for Luis and me, it's evening, and happy that you're all joining us for this evening session with Luis. And we have Transformer as a topic this evening. So what has Hackingface to do with Transformers?
So I think maybe Transformers is like in some sense as popular as it is today, partly because Hugging Face decided to open source a PyTorch implementation of the original BERT model. And this was a sort of paradigm shift in the field. And many people at the time were using PyTorch instead of TensorFlow, and they sort of really jumped on top of this library. And over time, this grew into GPT-2, but then suddenly, as many transformer architectures as were available. And I think this kind of created a snowball effect where around this application of transformers for NLP grew an ecosystem around building data sets and processing data sets in a simple way, and then also optimizing the inference side of these models, which are traditionally more complex than simple random forests or traditional, say, classical machine learning techniques.
Okay, that's cool. Guys, and still because we would like to focus a little bit on your interests, of course, here's some organizational things you need to know. You know, we're working with Zoom as a platform. There's a navigation bar, either on the top or below on your screen. And you find a Q&A section where a Q&A button. So each time you might have a question, click on it and just type a question in. We're going to ask the questions during the presentation, so we are not waiting to the end. Of course, there might be questions still for the end. And so you have time to do that all the time. Also, I'm going to start a little poll here now. You might see the question already. And we're asking two questions which help us a little bit, Luis and me, to see how the distribution of knowledge is in the community here. Now we can address what you need and your interests better. So yes, you can see already people answering it. That's fantastic. And it really helps us to focus correctly. Also, Luis just posted a link to a collab on Google. Before I'm going to type it in here again. Here it is. If you look in the chat, you will find the link. What can we do with that, Luis?
So this is a very simple demo of the kind of versatility of transformers. So it shows, and we'll do this in the slides itself, but it basically shows that with the same piece of text, we can analyze it from different dimensions. So looking at classification or translation or question answering and so on.
Cool. So it's something we can actually open next to a presentation, your talk.
Exactly. This will be the third part of the talk, but you'll see when it comes up and I'll let you know.
Third part, so it means we have 2 parts before it. What can we actually expect from your agenda? What's the agenda? 1, 2, 3.
Sure. So I'm going to try to kind of demystify a bit what transformers are, because this is sometimes presented in a fairly complex way. And this sort of second part will be about the Hackingface ecosystem I was mentioning and how this is tying into the whole sort of revolution in machine learning at the moment. Okay,
that's awesome. So looking at the poll, we have already so many people who participated. It's about 83%, so that's awesome. I'm going to share the results with you guys, so I hope you can see it. So regarding what is your profession, we have 34% who are actually working as data scientists, 15% software engineers. Welcome, software architects. We will not be forgotten. Welcome, product or project managers. Awesome. Academia is also very popular here with 22% and others with 23%. Sorry if I didn't mention your profession. You can also type it in the chat. I would like to ask more questions and better questions in the future. That's cool. So looking at the experience with Hackingface, I think probably a little bit like your experience, Luis. 89% are just beginners, so beginning with transformers and Hackingface. That's awesome. And it's open source, so that's cool stuff as well. You don't have to purchase it. That's a good thing. So yeah, I'm really looking forward. Just stopping the poll now. And yeah, since everyone is just waiting not for me to talk with you, just you to talk and present, take the floor. It's yours.
Right. I'll just share my screen. So let's see. Hopefully you can see this.
Yep, we can see it. It's perfect. Thank you.
Great. Just 1 second. I'm going to get a, where is this thing? This. Here we go, the mouse. Maybe I can use a spotlight. Oops. Okay, don't worry. I've got this like weird menu in the Zoom thing, but I'll just deal with it. Okay. So yes, thank you very much, Stefan, for the invitation to talk to you today a little bit about getting started with transformers. So if you're already a practitioner in NLP and you've been using transformers for some time, I can't promise you'll learn much that's new today. What I'm aiming today to do is really to sort of provide a gentle introduction to the topic and sort of try to answer a couple of main questions, which is like, sort of, why are transformers cool? Why or how do they work? And a little bit of like the sort of historical underpinnings of them. and then switching from that into sort of the Hugging Face ecosystem and how Hugging Face is enabling thousands of researchers and developers to be very productive with these sort of new types of models. And if you have any questions, just please dump them in the chat or just interrupt me. I much prefer people interrupting me than waiting till the end. So I think we can do a kind of jazz improvisation as we go. Cool.
That's so, because this is just our culture. Yes, and as I mentioned, click on the Q&A button, put in your questions. I will watch it and I will ask you questions. Thanks.
Yeah, so just a little bit about what I do at Hugging Face. So there are two main areas that I focus on at the moment. On the one side, it's education. So we've released a course just in June this year. And if you're interested in diving deeper into the subject, I recommend you click on this link and you'll get kind of a sort of real deep dive into sort of how the libraries work. And then if you want a really deep dive, there's a book coming out at the end of the year by O'Reilly, which I've been working on with Tom Wolfe and Leandro Fonvera. And this is really spanning everything from like the common tasks of transformers to how you train a transformer from scratch. And I think this should hopefully become like a kind of core reference in the field to help people get started. And then of course, yes.
If I interrupt you, but guys, since you're participating today and this is just a topic of interest, I invited Luis to have another talk about when the book is out. So we can have a talk about that as well. It will be later on, so not 2 weeks time, of course, so there's a little bit time in between. But Luis will be definitely invited to talk about that again. Thanks.
Great. Yes, and then the other side of course, Hugging Face is sort of founded on open source software. And a large part of my day-to-day job is around working or contributing to some of these libraries. And in particular, I've been focused on the datasets library and trying to sort of figure out how we can evaluate many of the models that are currently hosted in the Hugging Face Hub, which we'll explain a bit later. So let's see. Okay, so as I mentioned before, the plan of attack for today's talk will be roughly 3 sections. The first will be about a little bit of the background of transformers and sort of trying to explain the core concepts behind them. The second part will be about the Hugging Face ecosystem, and then we'll finish up with some kind of simple demos that sort of give you a feel for what's possible on the NLP side. So I think it's always nice to sort of show like how transformers are kind of already in the wild, so to speak. So an example you can see here is code generation from a product called Github CoPilot. And this was a model trained by OpenAI, which are a fairly famous company that has pioneered the use of transformers. And what it shows here is that if you provide basically the definition of a function in Python, and you give it like a doc string that says what you want to do in natural language, then CoPilot will attempt to autocomplete the rest of the function for you. And so you can see here that there's a little bit of highlighted text, and that's the source code that is generated by this particular transformer model. And this is still in beta, so it has some limitations, and it doesn't always work as you intend. But I've been using this for a couple of weeks now, and there are some cases where it kind of surprises you, and it's very good at doing like boring things like regular expressions and so on and so forth. So,
Luis, since this picture is very small, but you have a
yes.
notepad, can you just post the link in the chat?
Yeah, sure.
That would be awesome.
So I think I have to just do it this way. Oops.
That would be cool, so that everyone can actually bookmark it.
Let's see, where is the chat? Here we go. Cool.
Yeah, thank you. That's awesome. copilot.github.com. That's cool.
Exactly.
Thank you.
So let's see. I have to figure out, one moment. I'm totally a Zoom noob. Okay, here we go. All right. So I'm just trying to remove the chat. One moment. Okay. Okay, and so then another fairly famous example is from Google. So in around, I think it was 2019 or so, Google decided to introduce transformers, a particular transformer called BERT, into their search engine. And what they found is that by using BERT, they were able to get or provide people with much better search queries. And so here's an example where you can see someone has typed 2019 Brazil traveler to USA need a visa. So as a human, we can kind of understand that this is about someone who wants to go from Brazil to the US and they need a visa. And you can see that in the sort of old version of Google search, it was saying, you know, US citizens can travel to Brazil as one of the sort of top search hits, which is kind of the inverse of what you really want. And then by introducing this particular transformer model, the search results are improved, and you get something which is much closer to the intent of the user. And then another quite exciting one from a scientific perspective is there's a company called DeepMind, which has pioneered a lot of use of reinforcement learning and so on and so forth for computer games. But they've also done a lot of fundamental science. And just this year, they were able to show that if you combine a particular transform model to model sequences or amino sequences, you can actually like predict quite accurately how these amino sequences will fold into these complex structures. And there's a very famous kind of competition that is held in this field, and it's kind of like Kaggle for, you know, chemists. And basically DeepMind's model completely blew out of the water all of these previous attempts that were based on, you know, physics and chemistry and, you know, very kind of handcrafted engineering. So that was quite a big breakthrough in the field. So this is just a sort of taste of some high level applications, or say high profile ones. But there are many more that if you can find online. And the sort of first question that, you know, you might have is like, okay, what the hell is a transformer? And if you type what is a transformer on Google, you're probably going to see this crazy picture here on the left, which is the schematic for the architecture of this model. And this comes from a very famous paper called Attention is All You Need. That was essentially the sort of kickstart of this transformer revolution. But personally, when I first was trying to learn transformers, I sort of looked at this paper and I looked at this architecture, and this was basically my reaction, like, what the hell? I have no idea what's going on. And I don't, you know, really understand like what all these components mean. And so part of my sort of goal today is to try to sort of demystify a little bit what's happening in this diagram. And we'll see how far we go. So the first thing that you need to maybe just think about is that a transformer is a type of neural network. And obviously everyone here has probably heard of neural networks. They're a very effective way of modeling functions. So if we have a mapping of some input to some output, then neural networks are especially good at doing this. And they really kind of became very prominent with the kind of growth of like compute in GPUs and the growth of, you know, data with the internet. And so these kind of developments helped neural networks become deeper and sort of more performant in terms of their predictions. And so a transformer is just a neural network. And it's got a special twist to it, which is that it's specifically trained to model sequential data. So this data can be, for example, amino sequences, it can be time series, it can be, as we'll see potentially later, even video and things like this. But the most common sort of application is in language. And so you can think about one way that you have like a sequence in your text is that you might start with the word my, and you ask the model to predict what is the next word in the sequence. And so the model will have a range of predictions, and maybe the most probable one is name. And then you say, okay, you combine this together, and now you say my name, what is the next word? Maybe it's is. and you go on and so forth. And this creates essentially a process, or it's a technique called language modeling. And the basic idea here is kind of like the autocorrect on your phone, that you basically give some input words and the model predicts the next one. And it turns out that if you train these transformer neural networks in this particular way, they develop some basic statistical knowledge of how language is structured. So they learn about some aspects of grammar, some aspect of syntax and semantics. And then once you have trained the model in this way, you can then adapt to many downstream applications, whether it's classifying text or answering questions and so on. So these are like very high level concepts, but let's like dive a little deeper into how they work. So there are kind of three main things that drive the success of transformers nowadays. So the first part is this thing called an attention mechanism, and there are many different attention mechanisms, and we'll just look at kind of the sort of two most common ones. And then if you combine these attention mechanisms with this language modeling process I told you before, this is called pre-training or self-supervised learning, because you don't need any actual labeled data, you just need a huge corpus of text, like the whole internet, for example. And then the final component is something called transfer learning, where you take this, this model that has been trained on a lot of text, and then you adapt it to the task that you're interested in. And this is, I think, really where the success of transformers comes from, because it kind of opened a whole kind of set of opportunities for various things that previously were a little bit out of reach, especially in domains where you maybe don't have a lot of labeled data. So these are the three things that we'll look at in more detail. So let's think about these attention mechanisms. And I think it's nice to sort of remember that, you know, there was life before transformers. And in NLP, the sort of state of the art for modeling text, and particularly for modeling sequential data, were these specific neural networks called recurrent neural networks. And the basic idea in these neural networks is that you could have, for example, if you're trying to model translation, on the left-hand side, I have a sentence in English. I'm trying to convert it to German. So the basic idea of these networks is that you would feed the word one at a time into this thing called the encoder. And then you would propagate that information through this encoder and condense it in a single vector or a single numerical representation called a hidden state. So this state in the middle would basically represent numerically the whole input sequence. And then there would be a component called a decoder, which would take that numerical representation and then convert it back into you know, human readable text, which would ideally be the translation. And these models are quite old, and there are some very famous variants like the LSTM and so on. But they sort of had a kind of inherent limitation, which was that by collapsing all of the representation of the input sequence into a single vector, you have something called an information bottleneck. So basically, you can imagine that if I have like a very long piece of text that's maybe, you know, got lots of different people and phrases and all these things, if I try to represent that as just a single vector, my decoder has to do a lot of work to be able to kind of reconstruct that, for example, in the translated version. And so these recurrent neural networks in their kind of vanilla state, they typically suffered from this problem that they would kind of not really accurately represent the full input. And so an approach called attention, or a sort of a change to the architecture called attention, was developed. And the basic idea here is that instead of trying to represent the whole input sequence with a single vector or a single state, you would actually output all of the states from the encoder. So you would have an output state for every single word that comes in, or every single token. And then attention would basically weight these states. Basically, it would assign a different amount of importance to each one of these states. And then when the decoder has to reconstruct the translation, it would be able to figure out through training which of these input states are more or less important for generating the next element in the translation. So this provided at the time, much better translation models. And by the way, the whole story of like transformers kind of originates in machine translation, because at the time this was considered to be one of the sort of most difficult and interesting problems in the field. And so this attention mechanism, which is, you can just think of it as just a way of weighting vectors, it allowed these models to get a better understanding of word order. And so what you can see in this diagram is, yep.
Just a quick question about the concept of attention. So how can maths pay attention? Is it so? It's really just like attaching that kind of probability towards what might be the next word. Is that correct?
That's more or less it. So the basic idea is that when we feed these states into the decoder block, there's a cell called an RNN cell, which is one of these recurrent networks. And its job is to take all of these inputs and then output a word, basically. So in this case, in this image, it says sind. So it is trying to compute the probability that the next word in the translation is sind. But what it's doing is it's looking at the previous words that it has seen in its states, and it's working out, okay, based on what I've seen in the past, what should I use to assign the probability for the next word? Mm-hmm. So it's kind of like a weighted average of sorts. You're basically, you're trying to compute the probability based on what you've seen, but you've got to weight for each of these inputs. So they're not equally weighted as being equally probable.
Mm-hmm. Thank you.
Great. And so in this image, what you can see here is a visualization of the attention states, basically, between a French and English translation. So you can see that on the top, we have the agreement on the European Economic Area was signed in August 1992, .end. And this is the interesting thing about language, is that like word order depends or flips in different languages. So in French, for example, you switch European Economic Area into Zone Économique Européenne. So you've kind of flipped area and zone in the ordering. And so this is traditionally quite tough for machine learning or neural networks to master. And attention allows, you can see here that essentially attention is focusing, assigning these weights, which are like the highlighted blocks, to those three words. So it works out, I need to flip the order of zone and area so that I get the correct translation. And this is essentially the sort of reason why attention became such a popular component in neural networks. And it's not just for language, it's used in computer vision and in other domains. But there was a kind of inherent limitation at the time with this. So all of these recurrent neural networks, whether they're LSTMs or whatever, they explicitly have a sequential aspect to them. So you feed a word in, you propagate a state, you feed another word in, you propagate a state. And so you basically have a sequence that you have to model. And it turns out that trying to sort of scale these models up. So if you just say, hey, I want my RNN to go faster, can I just throw GPUs at it? It turns out that you're kind of inherently bounded by the sequential modeling component or the sequential computations. And so this kind of inherently limited the scale of data that you could train these models on, because it just it would take too long to train. And similarly, there was some sort of additional complexity in trying to really make these translations work really well. And you may remember that, like, for example, Google Translate wasn't traditionally very good. It's gotten a lot better. And a lot of that growth has happened because transformers came to the game. So, yep. You're on mute, Stefan.
You changed that. Now I'm back. Okay, so just because Mariam asked, and you have answered it in parts. She asked, has any attention been used for any computer vision application? You said yes, so you just mentioned it. Do you have an example for that? Sorry to interrupt you with that. We work on text, but have an example for using attention in the context of computer vision?
Yeah, so attention is, at least as far as I know in computer vision, it's often used when you're trying to do things like object detection. So imagine I'm trying to work out where the bounding boxes maybe are of different objects in my image, and their attention provides a way, especially when you have things like semantic labeling and stuff, where you're trying to say, oh, tell me where the dog is in the image. Then attention provides a way to sort of focus that context on the image. But I'm not a computer vision guy, so I'm sure there are many more applications.
I think it's a good point, so thank you. And Tran, because it's also the same thing, Tran is asking, I think different languages have different orders of words. Makes sense, yes, we know that in a sentence. Do we need to put our knowledge of such languages into attention mechanisms in some ways? Or does the attention mechanism will try to learn this order of words automatically?
Yeah, that's a great question. So the magic of this whole thing is that it's technically differentiable, we say. So basically you can compute, you can optimize these networks using gradient descent. And what this means in plain English is that we can train the model just by providing pairs of sentences. So English, French, just lots of these pairs, and it will learn like essentially the weights in the network will adapt through attention to figure out the word order. So you don't have to manually encode this into the model, which is the great sort of appeal, right? We generally want to eliminate as much handcrafting as possible.
Yeah, makes sense. Okay, thank you.
Cool. So the sort of main difference with the attention is all you need paper, where the transformer was introduced, is they said, okay, we know that RNNs have this limitation of needing to have sequential computations. Is there a way we can sort of get around that? And so they introduced an alternative variant of attention called self-attention, where instead of relying on the past to predict the future, they just allow the model to have access to both the past and future of the text, and attention would just be applied to every token in the sequence. So what this means is that if you look at this particular example here, on the left-hand side, you can see the connections between the words. So time flies like an arrow on the left and time flies like an arrow on the right. So these connections are just showing essentially the attention weights between them. And if we focus on a particular word like flies, then in the middle diagram, what you can see is that this attention mechanism is saying, the word flies has an important component in this sentence with the word arrow. And that's because time flies like an arrow is using flies like a verb. So it's kind of, it's sort of instructing the model, this is an important token you should pay attention to. And then this is what you, how you can disambiguate words. So for example, in the right-hand side, you can see another example where fruit flies like a banana. So now the word flies has nothing to do with flying like in the sky. It's just the insect. And so here, the attention or the self-attention mechanism is providing the context for the model to understand that actually the representation of flies is a mix of banana and fruit and flies. So this is the sort of main twist that the transformer introduced compared to the RNNs, where basically you can, every token or every word in your sentence is attending to every other word, which means it's basically a weighted average of every other word in the sentence. And to see this a little bit differently, here in this diagram, I've got the same sentences. So we've got time flies like an arrow and fruit flies like a banana. So they're kind of, the word flies is very different in both cases. And what we do in NLP quite frequently is we represent words with numerical vectors called embeddings. And so the idea is that if you have a numerical representation, you can then do computations on top of this. And so at the start, the representation for flies is the same. You just start with a sort of random embedding. They're just the same random embedding. And you wouldn't at that stage have any way of understanding or disambiguating the different uses of the word. And so then when you feed these embeddings through this transformer neural network, in particular through this self-attention layer, So this is just a layer in a neural network. You end up kind of mixing together all of the representations to create a new embedding, which is in this case a mix of, like, it's a mix of arrow and it's a mix of flies. So it's kind of like some representation of like a word like saws. And then, for example, on the right-hand side, the sort of output representation from the transformer network will have a different admixture of the inputs, which will then give you some sort of like representation of, say, insect or something like this. And this is sort of where the sort of, let's say, the magic of self-attention comes in, where it's able to provide context to the model so that you don't just have the same representation for the same word. It's actually, the representation depends on the surrounding words, and this is how you can then derive better translations or better classification. Yep.
We have questions again from Akram. Does attention understand the logical structure of the statement while translating, or does it just perform a literal translation word to word?
Great. So if we did word-to-word translations, we would have this problem with word order, right? Because, like, I wouldn't know how, like, you know, in the French example, European Economic Area is then inverted. So if we just did word-to-word translations, we would not get great results. So what actually happens in the translation case is you have your input sentence in English, for example, and every token, or a token is like a word you can think of. So every word in this sentence has a representation, a numerical representation, which is produced through this self-attention mechanism. And then you take these representations and you feed them to the decoder, which then uses the contextual information that they provide to then generate the outputs word by word, which, so it's kind of, it is doing it word by word in the generation, but it's using the contextual information of the inputs. I hope that answers the question.
Yeah, I think it does. And because this is also correct for that input, or context you gave, I'm trying again. So if each word will pay attention to the past and the future, and if a sentence has a length, and each word can relate to each word, yeah. So this is a huge mass of computing, right? So
exactly.
Will that become too expensive to compute, or too huge to compute, because the variation is so huge?
Yeah, that's an excellent question. So in fact, if we look at this image here, on the left-hand side, you can see all the attention connections between the words. And so in, say, computer science language, we would say this is order n squared complexity. So it's basically, I have to compute a matrix, which is n by n. Yes. And this traditionally is an inefficient algorithm. And since the release of the transformer, many alternative mechanisms, or let's say variants to attention, have been proposed to reduce this complexity to something like log n, or maybe n log n, is like the, but they require some additional like tricks to make this work. But you're right, the sort of naive thing is typically inefficient, but if you have a lot of GPUs, then you sort of, you know, you balance, it's like it's an inefficiency that you can live with. And just for comparison, in the original transformer paper, they were able to train state-of-the-art translation models, you know, many times faster than the previous state-of-the-art. So, and that was just, I think, on a couple of GPUs. It was like 4, maybe 8 GPUs or something.
Yes, thank you.
And yeah, so basically then the attention architecture, we saw this like very scary diagram at the start, but if we kind of really sort of dumb it down, we basically have, if we're doing translation, we have the same encoder decoder blocks that we saw for the RNNs, and you have essentially attention layers, and you have feed forward neural networks, which are just used to kind of improve the representations. And then you basically just feed all your inputs into the encoder, and then these are then fed to the decoder, which then, you know, iteratively generates the translations in this case. And as I mentioned before, because the attention mechanism doesn't have a sequential computation limitation, you can parallelize this with GPUs or TPUs. And this allows you to train much, much larger models than was previously possible. And so if you've heard of things like GPT-3, which is a very famous model from OpenAI, it has 175 or so billion parameters, which is enormous. You can't even fit it on a single GPU. But it's only possible to train such a model because you have the ability to scale with like a large distributed training infrastructure. And this gives you then much better models, because one of the lessons in the field of deep learning has been that generally scaling up the model in size gives you better results, or a better representation of the thing you're trying to model.
So sorry for a question again. But if you think of word embeddings, Christian is actually asking, are transformers based on embeddings, and also includes LSTM, or just a lot of embeddings?
That's right. So transformers, like let's think about, let's say, the left-hand side of this diagram. So here we have something called the encoder, which is basic. Its basic job is, if I give you raw text, give me numerical representations or give me embeddings. That's basically the job of the encoder. And so in this sense, the transformer is quite similar to, say, what LSTMs were used for, and even Word2Vec. But the key difference is that the embeddings are contextual. So in Word2Vec, the representation for like flies from memory is the same representation, whether it's a verb or whether it's an insect. Whereas transformers encode this contextual or relational information of the neighboring words, so you can disambiguate these representations or these embeddings. And LSTMs also were able to do this. There's a famous one called Elmo, which produced very great, excellent embeddings. But again, it had that limitation in compute. And so basically nowadays, most people who are using like these large transform models, they can use them to generate embeddings, which you can then build classifiers on top of. But although in my old job, I used to train my own embeddings using fast text, so I didn't use transformers, but that's another story. So it really depends on the application.
And coming back to the fly example, Yakis is asking, if we were to create embeddings with a self-attention model, can we assume the embedding vector of a word would carry the information of both contexts, or does it not work like a token dictionary way?
Yes, if the data that you provide in the training process has examples of the different uses, then it will learn different representations for these inputs. It will learn these contextual representations. So the basic thing is that you don't really think of representations in isolation anymore. You think about representations of a sequence. And so in a sequence, I have a list of words, and then the representations of those words depend on their neighbors or on everything else. Good question.
Thank you.
So now I'm going to mention now this like other component that sort of drives the success, or let's say the revolution of transformers. So we've talked about architecture, but architecture alone is maybe not enough, because in the literature there are thousands of different architectures. Why should I care about this one? So the other sort of change in paradigm, which was happening kind of in parallel to the transformer development, was this idea of what's called pre-training. So I mentioned this thing that we train transformers to model sequences of text. So you basically provide, let's say, all of Wikipedia, and you say, as I feed you this data, just predict the next word. That's your basic task. And then this technique is called language modeling, typically. And the results of this, or the process of doing this, generally requires a very large corpus. It typically requires days of training and is often quite expensive to train. So this is kind of like the first step to build a powerful language model. And once you have this, basically what you have is a very good autocorrect. That's more or less it. It's just very good. If you give it a couple of words, it will predict the next words with some degree of accuracy. However, you need no labels. So this is very kind of like human level cheap to train. You don't have to pay someone to label every single example. And this is great because in the era of the internet, we have tons and tons of text data. So once you have a pre-trained language model, the next step is to do something called transfer learning, or fine tuning, is also known way. And the idea is that you say, okay, I've got this amazing autocorrect model. However, what I'm really interested in is maybe sentiment analysis. Maybe I want to understand the sentiment of my tweets or something like this. And so then what you do is you take the kind of the pre-trained model, you take the weights of that model. So this has some basic understanding of language, grammar and syntax and so on. And then you provide essentially a set of layers which are designed for your task and some label data. So you do supervised learning, and you just kind of adjust the weights in just a little bit to adapt to your task. And this will typically give you a very performant model according to the metrics that you're interested in. And it has the advantage that you typically don't need a lot of label data. So if you think about traditional machine learning, we train from scratch. For example, if I'm building a classifier, maybe I do something like naive Bayes or something like this, and I have to train everything from scratch. In this approach, we take a model that already has some basic understanding of language, and then we adapt it to the task. And so this approach is fine tuning or transfer learning. And this is why transformers suddenly became very popular, because it turned out that if you just took a single model like BERT, you could then apply it to many different tasks, like almost all the core NLP tasks using the same basic architecture and the same pre-trained model. So it kind of saves you the time and effort of doing everything all the time from scratch. Great. So this was more or less the situation in 2018. And the kind of question at the time was okay, if I'm a data scientist in a company, or I'm a researcher, why can't I have access to this state of the art from Google and from OpenAI? And so there's a couple of challenges associated with getting access to these models. So for example, on the archive where all these scientific papers are posted, you will often find, for example, a link to some code and data. And this is a great, step forward compared to the old days where you had to email people to send you, the code. But it still doesn't really solve the core problem, which is that there are nowadays hundreds of different architectures and even thousands of different pre-trained models with different tweaks on those architectures. And you end up in a kind of maze of okay, which one do I choose for my task? And then, where do I even start from? And the other problem is that in open source, the kind of quality, or let's say the responsiveness of people can vary a lot. And so you'll often find libraries are implemented in Python 2, which is quite crazy. Or you'll get things like missing documentation, maybe the model can't be reproduced and so on. And so this is kind of, in some sense, the Wild West of, say, doing open source machine learning. And the question at Hackingface has typically been, can we do better? Is there a way we can improve the situation for the community of both scientists, but also practitioners who often, have this limitation of not being able to sort of have easy access to these techniques. So this sort of segues now into the second part about what is Hackingface. So Hackingface, of course, is a company, but sort of fundamentally, it's an open source company that is built around developing a community for artificial intelligence, not just NLP and transformers, but just more generally. So sort of broad field of machine learning. And we have a hub, which is basically the webpage of the company. And on this hub, you can find many different models. You can find different data sets. You have different tools for training models. And you have basically a wide range of tools that you can use to simplify the process. Mm-hmm.
Luis, just because that's good what you introduced in Hackingface right now. Shashank asked if he has difficulties with working with Hackingface models. Could you please tell us where you should begin to learn resources and so on? Is that the resource you're recommending to go to when you want to start with Hackingface?
Yeah, so my recommendation to get started would be to go to the course. So I mentioned this, it's in the first slide and I can share the slides afterwards. Basically, we have a course which gives you a kind of guided tour through the ecosystem.
Okay.
And then if you're very adventurous, then you can buy the book when it comes out, and then you can get very in-depth knowledge. That would be, of course, a sales pitch. So.
Yeah, sure, that's fine. I mean, it's fine that you wrote a book and you tell about it. And John is actually asking it a little bit in the same direction. Is there any officials YouTube channel for Hackingface webinars in English for NLP, and how transformers can be used for speech recognition, for example?
Yeah, so in the course, we have videos which are on YouTube. And I'll put these also in the chat, or I'll give them to you. But basically, yeah, there's a YouTube channel. You just look up Hackingface in YouTube and you will find all the course videos. For speech recognition in particular, I don't think there's a video on that. But if you look at the documentation of the Transformers library, you'll see examples, and there's also tutorials in the documentation on training these speech recognition models.
Okay, cool, thanks.
Cool. So as I was mentioning, we're fundamentally an open source company. And so we have various libraries which are developed to essentially provide tooling to simplify the process of training, not just transformers, but broadly speaking, machine learning models. And as part of this ecosystem, we also have a library called Datasets, which is a highly optimized library for processing large data sets very quickly. And then there's an Accelerate library, which is used for sort of helping your multi-GPU training become simpler. So if you have large models, you typically need multiple GPUs. And again, traditionally, if you do this natively in PyTorch, it's a bit of work, and this library just simplifies that for you. So this is kind of the whole picture at the moment. This is accurate as of today, but the hub moves or let's say the ecosystem evolves very quickly. So maybe tomorrow it's different. But I'm not going to cover everything because it will take us, several hours. But the basic thing I would like you to sort of just take away is that there's this hub that we use as kind of a central repository for models, for data sets, and for interacting with the libraries. And we have on the one side, on the left, we have open source libraries, which are, as you say, free, anyone can use them. And we also provide some paid services. For example, AutoNLP allows you to train these models without even writing code. So you can, there's a UI, you can just click some buttons and then you can train transformers. And then there's a SageMaker, essentially say service that allows you to efficiently train these models on AWS. And then of course, there's the whole sort of optimization inference side of things, which I won't talk about, but that's also part of what Hackingface offers to people who are interested in making their models run faster or run at scale.
If you want to use the free model, is there any kind of data quota limit or something like that? So that's the limit, and upload up to them?
No, so for uploading and downloading from the hub, there is no limit. The only limits we currently have for people who sign up are access to, say, the inference API. So if you have your model in the hub, you can just download it onto your laptop, and of course you can generate predictions. But in many applications, you would like some API that you can just send requests and get the predictions from. And so for that, there's a quota based on the pricing plan.
Okay, thank you.
So in this hub, we have all these models. And as you can see, there's around 22,000 models spanning not just transformers, but spanning now things like Spacey, even some fast AI models are starting to be posted here. And the kind of aim is to try and make this a sort of central place where people can share and collaborate in machine learning projects. And the whole goal or ethos of this is to just make this process as simple as possible, so that you don't have to, write tons and tons of code just to get started. And there are also some kind of other interesting things you can play around with. So one recent thing that's open sourced is called Spaces, which allows you to basically write a very simple web application like in Streamlit or Gradio. and then you can basically build an interface to your model. So you can very quickly, see the predictions of the model and, feed it predictions. And this is, traditionally, previously I used to work as a data scientist. This was always like a kind of common bottleneck of like, you want to demo the model to someone and you have to then build your own, Flask application or something. So there's the sort of tokenizers and transformers libraries, which are kind of the focus of this talk. So I just want to show you just quickly what this is about, and then finish with some sort of very quick demo, and then we can, go to a broad Q&A about, the meaning of life and so on. So,
okay.
So the transformers library is where this basically all started, and the sort of design of this library has been around supporting as many different architectures as possible, but using the same API to do that. And so here you can see in this example with more or less 2 lines of code, you can download from the Hugging Face Hub the original BERT model from Google, both for the tokenizer, which converts the text into these numerical representations, and then the model, which is then used for generating or for training or doing predictions or whatever. And so this API spans more or less over 50 architectures and roughly over 15,000 models on the hub. And so if you look on the hub, you can find different examples and play around with them. And this is a little bit more lines of code, but more or less this is what it takes to train a transformer or to fine tune a transformer on your domain. And so here you can see an example where we load a BERT model, which is the pre-trained model, which doesn't really have any specific domain-specific knowledge about, let's say, sentiment analysis. And then you can provide some sort of basic hyperparameters to something called a trainer, and then you provide the model and the data set, and then this allows you to basically train and push the model to the hub with just a few lines of code. So probably if you've used transformers, you're familiar with this, but this is, again, this idea of having a single API that you can use and just swap out the name of the model and experiment quickly. So just to wrap up with a couple of sort of very simple examples, but just to show you the versatility of transformers. So there's a pipeline which kind of wraps all the processing around converting text into numbers and then converting numbers back into text. And here I've got an example which we'll just use. Imagine that I'm like an Amazon customer support employee, and I get a message like this which says, "Dear Amazon, last week I ordered an Optimus Prime action figure, and when I opened it, I discovered I was sent an action figure of Megatron, and I'm a lifelong enemy of the Decepticons, and so I'm really annoyed, and I want you to exchange my Megatron for Optimus Prime." And you see that it's signed by Bumblebee, who is one of the original Autobots in the Transformers TV show. So you go, okay, I've got this thing, and I had to read all of that to get some understanding of what's going on. And a common application in industry is to classify text into sentiment. Is this a positive or negative response? Because then I can maybe filter them and just focus on the negative ones. And so here you can see that I can feed this text into a sentiment analysis pipeline, and it tells me with 90% confidence that this is negative, which is kind of consistent with what we read. But it turns out that you can use transformers to do other sort of more elaborate tasks. So a very interesting one is something called question answering, where the idea is that you pass the text that you're interested in analyzing, and you pass a question. So in this case, we can ask, what does the customer want? And the model will basically read the text and figure out which span has a potential or candidate answer. And so here we see, what does the customer want? And it's figured out an exchange of Megatron, and it's told us where the start and end of that piece of text was in the components. So this is an example of the versatility. We're using the same text, but we're looking at it from 2 different tasks. And then another one is translation. Maybe I work in Germany because it's German Amazon, and I don't want to read this English stuff. So again, you can feed in the text, and the translation is pretty good. I mean, my German isn't perfect, but it looks pretty good to me. And this is impressive because this is quite a long piece of text with lots of, context, right? I mean, you've got the thing about the action figure and who the person is. So, there's a lot of sort of reasoning that is involved in decoding this into a German translation. And then the last one, which is just for fun. We saw at the very start of this talk, there was this example of code generation from OpenAI. And this originates from text generation, where you say, if I provide some input, can I just auto-complete this, keep auto-completing and see if I get some kind of creative output? And so if you've used autocomplete on your phone, you know very quickly this just goes into gibberish. But some of these transformer models are actually quite good at understanding the context of like the input and then figuring out like, if you provide a little prompt, like, in this case, the prompt I'm providing is like a customer service response. I'm just adding that little piece of text, customer service response. So the model is taking the customer complaint, a text which says customer service response, and then it's working out, you want me to generate a reply. And so here you can see the reply from the model is, Dear Bumblebee, I'm sorry to hear that your order was mixed up. The order was completely mislabeled, which is very common in our online store. Blah, blah, blah. So this is with no labeling, no label data, it's worked out that, because I gave it a prompt of customer response, it said, you're telling me I should generate a response, and it generated one. Now, maybe I wouldn't deploy this because, things can go crazy, but it just shows you a little bit the versatility of what's possible. So I've kind of been telling you all these great things. Yes?
Because we have an integration question here from John again. I often use PyTorch Lightning to do research, production, and scale training, etc. Is it easy to integrate Hackingface transformers or ecosystem with Lightning seamlessly?
Yes, as far as I know. I haven't personally done it myself, but I believe it's straightforward. I think you can just wrap you have to use this Lightning module, so you probably have to sort of wrap the transformer model somehow. But just fun, this is going to be very technical, but just for yarn. So at a fundamental level, everything in transformers is NN module. So it's basically this core class in PyTorch. And basically, I think with that, it should be more or less compatible with PyTorch Lightning.
And the last question, this one is from me. This is more maybe a philosophical nature, if you go back one slide. And it's basically the thing which, what's behind this attention thinking. And correct me if I'm wrong, but basically, since we would like to predict the next word based on statistics, so what's the probability of the next word to occur? We actually build a kind of bias in the model which says, okay, we have this general thinking, the hypothesis is the next word needs to have a higher probability to be suggested. This is in contrast to creative writing, which means the next word might not be the most probable, but the most likely, I think, might be best for the context of the scene I'm describing in this example. So this is maybe the kind of thing where we can see, well, that's the limit of creativity with kind of those tools, which do some suggestions. Yes, they do, but it's not a creative one. It's just one built on massive data. And that's likely that this happens. Okay.
Exactly, and I think perhaps, it's interesting to see like what other limitations of creativity in machine learning. So you're totally right about saying that you encode the bias. So for example, I think the original GPT model from OpenAI was trained on a lot of books, and it has some romance, like it had a bias for romance novels. And so if you provide it with like a prompt, like, Bob and Alice walked into a bar, it will typically complete a romantic encounter because it has that bias. But then GPT-2 was trained on Reddit, and then it has a different type of bias. So it typically absorbs, some aspects of the way people write on Reddit. So your creativity is somehow bounded by the domain you train on.
Yes.
But one very interesting aspect of this I've seen is that people have used these models to generate poetry, for example, and there the creativity is coming from the human operator. So the human operator is guiding the model by kind of configuring the parameters for the generation. And then they're using this to kind of work out, okay, can I get the model to generate something interesting? And, you know, there's even a company called Latitude that has a product called AI Dungeon, which creates full-scale fantasy worlds like Dungeons and Dragons, where you can interact with an AI and it will generate the next action or task you should take. Kind of like a choose your own adventure thing, but purely entirely simulated.
Yeah. And the last additional part to what you're saying today, sorry for just interrupting you again. One thought is I was experimenting with GPT-3 with API, and I got to know Ort. Ort was invited to present at our episodes as well, introducing the kind of think tank simulation. So can you ask a question and you give back some suggestions of what you could do in terms of asking a question which makes sense in the real world? So can it be used as a kind of think tank application? So that was interesting. It was just like, hey, that's cool. If that works, how crazy, that would be really crazy. And I tried it with an example from my world, of the business world and dental market in Switzerland. And it just asked, like, how large is the dentist market or the dental market in Switzerland? So teeth, tooth, right? And this was interesting to see the answers. And sometimes when you, I think I did it a day later, I got a slightly different answer. And this, I think, is also typical for those models. You get an answer, yes, and it's maybe correct if the data is correct, yes. But you won't get the full picture you might get from someone who is actually in charge of doing a report and writing out the data together because you need it. So this is the limit.
Definitely. And you're also fundamentally limited by the data that you were trained on. So for example, like I think maybe COVID, right, probably broke thousands of machine learning models because they had zero context of like, you know, what is this word even in, you know, my vocabulary.
Yeah.
So this is, I think, maybe like the fundamental limitation of current machine learning is like, how do you adapt rapidly to these changing events? And, you know, of course you can just retrain the model, right? You can just always just collect more data and retrain, but this is typically, you know, progressively harder when the models are very large, like GPT-3. Yeah. You can't just train it, you know, every day.
Yeah, sure. And so that's a good point that we just stopped here because we have many questions which are more practical ones which fit perfectly here. So Mirel, for example, is asking, is it possible to fine-tune the pipelines?
No. So pipelines are for inference, basically. Inside them, there is a model and you could fine-tune the model. But the traditional workflow is that you first take a model, you fine-tune it, and then you wrap it in a pipeline.
Saul was asking, can I use, but I think that belongs to one of the last slides before you started introducing Hackingface. Can I use different activation functions in the output? He was asking.
Yes, so, and this is what the researchers experiment with a lot. So you're probably familiar with like ReLUs, and yes, there are things like JELUs and CLUs and so on and so forth. And yeah, many different architectures have different activation functions. But from what I recall, there was a paper earlier this year that was analyzing kind of like, you know, all of these different permutations of like, you know, does it matter if I like change the order of the layers or do blah, blah, blah. And the conclusion more or less was that the original transformer is basically good enough. Like all these extra things that people have played with, they help you, if you're a researcher, get a little boost on a leaderboard, you know, on a benchmark. Yeah. But from a practical perspective, you can just use the defaults.
So it's Pareto, basically. You say you can do much less and just have a good result in the end.
Yeah, exactly. I mean, introducing these additional activations maybe introduces complexity, which is, I mean, not always, but maybe it does.
Yeah. John is asking, when you use transformers to generate text, I think in some cases it might generate wrong grammar, syntax, and so on. Does transformers provide any kind of models to fix these grammar mistakes? or is it just basically the massive data which is fixing it in the end?
Yeah, so this is a sort of a very like a broad topic called, let's say, text generation, just broadly speaking, not just about transformers.
Yeah.
And the way that you decode text is not unique. And what I mean by that is that there are different strategies for converting an input sentence, like my name is so-and-so, figure out what to do next. And I was telling you before that we select like the most probable token and then we just autocomplete. But that's like a simplified picture of basically algorithms that are used for figuring out what is that next word. And there are parameters associated with these algorithms. So you may have heard of things like greedy search, which just picks the highest probability all the time. That's got 0 parameters. It's just very simple. But then there are things called beam search, which have a different strategy for figuring out what is the most probable token. And then more sophisticated ones that use things like sampling to figure this out. And so there's always parameters associated with text generation. And this is where a little bit of the black magic comes in, where you have to tune these parameters to get things to be closer to what you want. So some parameters will typically produce more hallucinations or more creative text. The model is kind of, high on marijuana or something. Mm-hmm. And then if you change those parameters in a different way, it will get much more deterministic or let's say more closer to like, say, producing like, say, factual or correct statements. And it's really up to your use case of what you want. But there's no, as far as I'm aware, there's no, universal recipe for doing this.
I think that was a perfect quote, high on marijuana. That was awesome. So Simon was asking, does the nature of the data sets for pre-training and fine-tuning have to be the same? For example, can a transformer pre-trained on language data be used for another purpose, say for Boolean folding data?
That's an excellent question. So the simple answer is generally no. And the reason for that is if the domains are very different from each other, the vocabulary, for example, can be very different. So if I imagine that I train a model on Wikipedia, then in the model will have some finite vocabulary, which is basically the words that, or let's say the tokens that it knows how to represent. And these are generated from the corpus itself. So you look at the kind of statistical frequencies of words, and then you work out, okay, there are algorithms for doing this, but basically you work out which like words or tokens are like the most representative in my vocabulary. And then if I switch to something like protein folding, I'm suddenly dealing with like a very different domain, and the vocabulary there is just fundamentally different. I've got, all these AA, GG characters. And so what will often happen if you try to do that is the performance of the model will be very bad. Basically, the model will fail to capture the sort of intrinsic, you say, bias, basically, in the target data set. And this can happen, for example, if you want to study law documents or whatever, you already have a domain-specific language in law, or if you switch from languages, right? I mean, there are all these kind of things where, like, if you try to take an English model and go to German, maybe it does okay because German and English are maybe some overlap. But if you go to, say, Japanese, it's a completely different character set and the model will fail atrociously.
Yeah, exactly. So Christian is asking, what do you suggest to non-English language-based tasks? And yes, I think most of the examples are usually English. And so everyone who's not English speaking as a native language is think, okay, but what's about my language? Should we translate to English and then analyze, or should we retrain to our language and specific corpus?
That's a great question. I'm going to actually switch to the slide because this is, I think, the thing where I want to talk about the limitations. Cool. And so, yeah, like, of course, I've been sort of saying how awesome transformers are, and they are cool and exciting, but they have some fundamental limitations. And this thing about, like, unfortunately, the world, English is, like, in some sense, the dominant language, both like in spoken proportion, but also in written proportion. If you look at internet text, it's highly dominated by English websites. And then there's a tail where you have languages. I think German is maybe number 2. And then there's like some of the European languages like French and so on. But then, you know, as you go off to, for example, let's say Romansh in Switzerland, I mean, there's only 20,000 people that speak Romansh. And so the amount of written text for that language is very low. So what I have typically done in my previous work there are multilingual transformers that exist. And so a very famous one is called XLM Roberta from Facebook. And this model is trained in parallel on 100 different languages at once. So instead of just picking, let's say, English Wikipedia, they pick Wikipedia of like 100 languages plus internet text in these 100 languages. And then the model is able to learn these kind of general representations across multiple and very different things, you know, Japanese to German. And so then if you take this kind of multilingual model, you can then fine tune it on your domain or your language. And so this in my previous work was often quite successful. You could take this model and then you could fine tune it on German or French or Italian. And in some cases, you could just fine tune it once and then just apply it to French, and it would also work quite well. So these multilingual models exist and are quite good. But what people have observed in literature is that if you have a monolingual model in your language, this will typically be better than these multilingual ones, because the multilingual ones have to sort of, you know, master all the complexity of multiple languages. So if you find one in your language, you're good. But I know from experience that is often quite hard. Outside of German, French, Italian, it starts to get tricky.
Mm-hmm.
Great. So I think I'll just finish with like a few sort of extra things that are these limitations. So the other aspect of transformers is, like I was kind of talking about, you know, fine tuning itself typically doesn't require a lot of labeled data, but the pre-training process does. And this is where you need to typically have something that's like on the scale of, like, you know, Wikipedia or above to generate a good enough model in say that language. And this has limitations, again, of course, for all these languages that are not supported, but also for domains that maybe are interesting. So for example, maybe I would like to, I don't know, produce a model of mathematics or something that, you know, can a transformer for mathematics. Then I need to figure out how to get a corpus of that. And that's, again, not so easy. And then the other aspect is that these models are in some sense, you know, they're neural networks, and neural networks have this kind of, you know, reputation of being black boxes. And I think what people mean traditionally by this is, like, if you come from like a modeling background, so if you've ever, you know, remember your high school, say physics, you remember that there are these like laws, like, you know, Newton's law, like F equals ma. And this very simple mathematical statement can be then applied to a diverse range of phenomena, from gravitation to, you know, optics and things like this. But you have a very clear understanding of like the influence of those terms. So, you know, if I change the mass of the object, I can understand how that influences the force. Whereas neural networks have nowadays, you know, millions, billions of parameters, and we don't have yet the tools that allow us to very easily inspect the sort of like why the decisions were made. So we don't really have yet the ability to sort of deconstruct or reverse engineer the decision making. Even though there are people working on this a lot. But this is important, right? If you're doing like healthcare or any sort of high stakes decision making, a very common thing people ask for is like, okay, why was the decision made? You know, for example, if I need to make a diagnosis for a patient, you want to make sure that you're not just saying, oh, model says X, and then, you know, that's it.
Yeah.
So this is, I think, a general limitation, and especially for transformers, because they're quite complex models. And the last one, which is worth mentioning, is this thing we briefly touched on about biases. So transformers will encode the biases of the data they're trained on. And that bias can be like innocent. It can be, for example, romance novels versus scientific literature. But typically, because these very large models are trained on like the whole internet, or, you know, very large aspects of the internet, they will typically pick up all of the racist or sexist text that is written. And this then can propagate stereotypes, you know, in the generation, for example. So there are like some famous examples from GPT-3, where if you prompt it with like, a Muslim walks into a bar, it will typically associate that with terrorism. And that's just encoded in the bias from the data it was trained on. And this, of course, is not a stereotype we want to propagate. And so I think this aspect of like the bias of these models is a very sort of important topic at the moment. And it's going to be interesting to see how the field kind of works around how to handle this, because the data sets are so big that you can't remove all of the negative data. And at some level, you might accidentally remove important aspects of the human experience, just accidentally. So this is something that is worth mentioning. And it's also something to be aware of when you're using these models in your day-to-day job, that you really inspect what the outputs are and make sure that you're not, accidentally, automating some, negative side effects. And yeah, I guess we've had lots of questions, but if there are more questions, I'm happy to answer them.
So thank you for Luis, just for all the inspiring moments we had. Already, it was just fascinating talking to you. Yeah, Mariam was just asking anything that doesn't include sequential data. So more when doing the sequential stuff.
Yeah, so actually, there are some interesting developments in tabular data. So kind of traditionally, neural networks haven't been really optimized for handling tabular data. And there's a model called TAPAS, which is can basically extract answers to questions from spreadsheets. So if you have an Excel spreadsheet with some numbers in it, for example, you can ask, what is the average of my quarterly sales or whatever? And this model with some reliability can compute, these mathematical operations on tables. But the training of the model at some sort of fundamental level is almost always mapped to a sequential problem. And that's just primarily because of the way this attention mechanism brings us benefits. It typically needs a sequence so that it can apply this attention mechanism and generate these kind of rich representations. So yeah, off the top of my head, I'm not sure of let's say totally non-sequential examples. For example, in computer vision, you have an example which doesn't obviously look like a sequence, and transformers are now becoming very important in this field. But what you see that people do is they take an image and they then unravel it into a line of pixels or patches of pixels, and then they apply the same tricks on these patches, and then they generate these representations. So yeah, I think a very interesting question is, is that it? Have we reached the bottom of the architecture layer? And it'll be interesting to see if my book is obsolete in 2 years' time or not.
Yeah, and I told you what you have to present it once it's in the store.
Yeah, definitely.
And so the last question from John, it was going back to the initial questions we had regarding the computation stuff, right? But it was obviously, maybe we were too fast, but he would like to get, again, some tricks to deal with computation expensive Luis, computation expensive computing here in that context, yeah? Any tricks, how can we deal with data structure, pipeline, whatever?
Yes, so I think there are two sides to this. One is the training of the model. And this is typically where you need to worry about, let's say, GPU computations.
Yep.
And the main, let's say, challenge you'll face is that you're somehow limited by the architecture that the model was implemented in. So unless you're training your own transformer from scratch, which is actually pretty rare because it requires a lot of compute, you're typically limited by the computational complexity that is provided by the pre-trained architecture. So for example, BERT has this order n squared complexity, but then there are these variants like Big Bird, which are much more efficient. And so then you can use these different architectures if that's really important for the use case you're trying to solve. And then yeah, if you really want to know the details, you can look up, for example, the Big Bird model, and then this will have references to all these tricks that people are using. Just to give you like a taste of what people do. We talked about this attention mechanism is basically computing a matrix of like relationships between all the words in my sequence. So for example, time flies like an arrow. I work out, what is the relationship between time and flies. So you have this kind of square matrix.
Yeah.
And so the tricks that people do is they try to sparsify the matrix. So they say, okay, maybe we don't need to compute every single entry in this n by n matrix.
Yes.
And this sparsification process, then there are different ways of doing that, and that can be faster than doing the computation. And the other one, which is widely used, is you try to kind of change the order of operations that are done inside the neural network or the transformer architecture, so that instead of computing this matrix just in this like naive way, you compute some previous quantities which make it faster. But yeah, if you look up Big Bird, the model, it will then reference all the other previous works. And then just to wrap up, on the other side are the computations for inference. And these are different because typically you can run this on a CPU or even a GPU. And then the problem you face is that you're basically trying to do matrix multiplication as fast as you can. And so then there are techniques which you can use to make the model smaller. So you can basically reduce the number of parameters it has. That's called quantization or pruning. And yeah, there's a whole range of techniques that you have to think about there.
Yeah, thank you. It was interesting that you mentioned Big Bird. So that was in the chat as well mentioned. That was nice. One last comment here regarding language. I think language is conditional. What does it mean what I'm saying? So it's not just any word can be related to any word. That's just not the case in reality. So the interesting thing is that some words have a condition that they appear with certain context words as well. And this world is just not as free as we think. It's really much more determined. And the interesting thing is, and that's what we're actually working on, is that also if you have future changes. So let's take a real world example: nuclear energy, nuclear power. It's completely different discussed in Germany, for example, which is actually saying nuclear power is a no-go. We have to stop it. And other countries like Poland have started to build up nuclear power again. So some countries didn't have, or maybe the societies might have less problems with that. So that's a completely different discussion, which means we have a different kind of adjectives related to nuclear power, a different kind of story and narratives related to a term. And this is interesting, and I think this is not represented by the current language models, because this is just like we take everything in, digest it all, and try to make sense of something which might come out of it, but less about the conditional stuff, and because any kind of word is just conditional in my context.
Definitely.
Okay, there's one question from Mariam I see left. Would you please share the title of the paper you discussed at some point? I'm not really sure which one, but Mariam, I can tell you, Luis is on LinkedIn. So.
Or Twitter.
Okay, he's on Twitter. That's even better. If you can type your Twitter handle, Luis, that would be nice.
Just one second.
Because a few people asked me during in the chat, basically, not in the Q&A section. Yes, so the recording will be available. Usually we are quite fast. So David, who I mentioned in the beginning, is helping me to do that. Thanks for posting the Twitter handle. So the recording will be probably up tomorrow. So you can, at any time, you can just watch it again or rewatch parts of it if you like. And as you now have Twitter from Luis, can always ping him on tweet to Luis on Twitter. That's nice. And yeah, that's it. Thanks for everyone. And yeah, one thing, Luis, you need to send me the presentation slides so we can.
Sure.
It. That would be
I'll do it straight after this.
Cool. So thanks again. I think it was awesome. I was just, it was great. It was just coming so many questions. I was like, wow, that's cool. And I think this is really a hard topic, and we definitely have to continue with discussing transformers. And I say thanks again for everyone who just attended, and for the great questions you had, for staying with us for a long time and for patience. And thanks for taking your evening time, Luis. So it's a private time as well.
No problem.
And for sharing your expertise. Look here, the thank yous coming in. Thanks for sharing your time. Thanks. Enjoyed it, really enjoyed it. So this is cool. So have a nice evening, have a nice day, afternoon, morning, whatever you have, wherever you are living. And happy to see you again. Next week we will have, we talk about China and natural search, using all of the neural networks for building a search engine, which is also open source. And I think also great stuff. Happy to have you here and welcome you soon again. Nice day, and thanks, Luis, again.
Thank you, Stefan, and thank you for everyone for coming.